Okay, so boys and girls, imagine this for me. You've got two computers that are now connected to a network. Zach and I have connected our computers, and Zach needs to send me a file. Anyone have any idea what the hell, what happens there? What's going on? Pretty big question. Go for it, Zach.
Beams it over the waves.
Beams it over the waves, if it's wireless, 100%.
If it's wired, you're sending information over the wire to the other computer.
Absolutely spot on. In what form is that data being sent over a wire?
Binary.
It is binary, yeah. And how do we represent binary if we're sending stuff over a wire? Highs and lows. Electricity. Yeah, Zach, did you want to jump in?
Yeah, by just having electric pulse for yes, no pulse for no.
Now there's the question. It's a high volt for yes, absolutely spot on, 1. Can we have a no pulse for 0?
No, it
Wouldn't receive anything. So it's actually a very weak strength or weak pulse in that sense. High pulse for 1, weak pulse for a 0. So everybody, jump with me for a second. This is our lovely little diagram. We've got lovely computers all connected together. Does anyone know what that thing in the middle of them is called? It's not a server, but that's a nice try. Could be a router, could be a modem. Operator, interesting term. But when we have more than one device connected together, guys and girls, that's when it starts being called a network. And what is the purpose of having a network? So multiple devices could be connected, spot on. What else? Why else would we put multiple devices together in a network?
Information can be shared on a lot easier.
And that's 100% why we do it, to share information. That's why things like phones were invented. So we could actually send information to each other, send messages. And you might even want to synchronize applications, such as playing video games together. Okay, that happens over a network. When you guys and gals have got a small collection of computers all together in a relatively small space, we call that a LAN. What was that, Sam?
local area network.
Absolutely spot on. Anyone been to a LAN party before? Don't be ashamed. Put your hands up if you have. Yeah, love your work. So that's where it comes from. A local area network is literally just that. Multiple devices connected in a local space. Now, boys and girls, when we start taking multiple LANs and making bigger networks over larger spaces, we then create what's called a WAN, or a wide area network. So I've got a question for you. A couple of questions, actually. What would the school here be? Got vote for WAN over here. What else? There's only one other option. It's actually a LAN, purely because the space isn't that big, considering it's a kilometre or so from front to back maybe. But yeah, that's still considered a LAN. However, when we take multiple schools around the region and put those together for the Department of Education, that is a WAN. Alexis?
Do they have a specific, it has to be this many kilometres away, or is it just a general?
It's a very loose sort of term in that sense. It's a good question, but yeah, when it goes over a larger space, we tend to go, oh, it's a WAN now.
So WAN would be like all paths.
Yes, yeah, exactly. Or what's the biggest WAN anyone can think of?
The global internet.
The internet. I'm glad nobody said World Wide Web, okay, because World Wide Web has nothing to do with a LAN or a WAN. Now, when we start connecting all these devices together, boys and girls, they've got to start communicating. They've got to be able to send messages to each other. And there is a special term that we use for these messages. We call them data packets. So imagine, well, it's ones and zeros, isn't it? Computers think nothing but ones and zeros. So when you take these ones and zeros and you package them up, you create a packet of data. And then you flick it to the other computer, that computer unpacks it, reads the data, packages its own little messages and sends it back. Sound pretty good?
Yeah.
However, if Zach is sending me a giant video file, let's say he's sending me something that's multiple gigabytes in size, computers don't like that. They don't like huge messages because huge messages can get lost, corrupted, deleted, whatever. So they just do little packets. Okay, we're talking hundreds of kilobytes at a time. So Zach's video file will be chopped into little pieces and it would send me all those packets, and then my computer would have the job of reconstructing it as a bigger file on the other end. Okay, and this is the biggest thing I want you to take away for everyone. So eyes up here for a sec. A data packet has 3 components or 3 sections to it. You've got the header, which obviously comes first. You've got the payload, which is in the middle, and then you've got the trailer at the end. And the purpose is pretty simple. The header is information about the packet coming in. The payload is the information that Zach is sending me, the video. And then the trailer is basically to indicate we're at the end of the message. Okay? I'll pause there for a sec because there's a lot of concepts in those last couple of slides. Let's just get back to this for a second. So we've got 3 parts to our data packets, yeah? Let's quickly have a look at what is actually inside these data packets. Remembering it's all 1s and 0s, yeah? Everyone's good with that? Now, Alexis has asked me an amazing question, and basically it is, what is the biggest size, or how much can we put into a packet? And I'll tell you that in just a moment. The header section, which is obviously the portion at the front of our message, tells us these things. It has basically what's called starting bits. And your computer, when it receives a packet, it looks at the first couple of bits and it looks for a very specific pattern. If it doesn't see the pattern, it actually just what's called drops the packet. And that's basically just deletes it and gets rid of it. Okay? If it sees the correct pattern of bits, which funnily enough, for a normal Ethernet packet is 101010 16 times. Pretty good. The next one is the length of the packet. Okay, how long is this packet in size-wise? What is the packet number, just in case this one got split into multiple packets? So is this packet 1 of 3? Is it packet 2 of 3? Is it packet 3? And what's the identifier? Basically, if something does get chopped into pieces, it's given a unique name, numbered 1, 2, and 3, and they can be set in any order to Will's computer, and Will's computer can put them back together in the right order. Next one, what protocol we're using, we'll get to that in the future. Destination address, where's it going? And origin address or source, it's mostly called, where did it come from? All right, so is everyone okay with that? It's just information about the packet. Then we've got the guts of it. What actually was sent? Is it the video data? Is it the body of an email? What is it, essentially? And the trailer is pretty straightforward. We've got some error checking bits to make sure if any 1s and 0s got corrupted along the way, that we can detect if that happened. If it got corrupted, we drop it and we ask for another one. Okay, and then we've got stop bits. The same thing as the start bits, a little bit of a pattern to say, this is the end of my message. How's that so far? Very generic, isn't it? What about something specific? All right, there's my little data packet at the top there. And to give you an idea, this is not the proper size of a data packet. The proper size of a data packet is 20 bytes minimum or 60 bytes maximum. Any mathematicians can quickly do, a byte is how many bits? 8. So what is 20 times 8? What was it? Beautiful. So the minimum size of a data packet is 160 bits. You do not need to remember this, by the way. This is 480. Not a lot of data, is it, per packet? It's tiny. If you send a text file, you might be right, but if you're sending like an MP3 song, that's automatically going to get chopped up straight away. Sorry, Taryn.
What happens to anything smaller than the minimum size?
It's called a runt, and it gets thrown away. Literally, that's the term they give them. If there's smaller packets than 20 bytes, they go, that's a runt packet, see you later. If it's bigger than 60 bytes, it's called a giant, and they throw it away as well. Alexis?
So what happens if you want to send something, but they've all hit the maximum and the next one is below the minimum? Does it just cut off the last bit of data and delete it?
So when I say the minimum is 20 bytes, that includes the header and the trailer as well as the payload in the middle. So generally speaking, a header and a trailer by itself takes up roughly 20 bytes. And then anything on top of that is just the payload in the middle. Does that make sense?
Yeah.
Cool. So if you have a look at this weird data packet I've got going up here, a portion of this is going to be dedicated to the, the header. And that's going to tell us the start bits. It's going to have the destination, the origin, the protocol, the identifier, and the length. So obviously not a real example because that's way too short. Okay, and on the end, these would represent the trailer, and that tells you the error checking bits and the stop bits. And then everything in the middle, what do we call that again? Payload, yeah. What are we sending exactly? Seems like a lot of wasted data, doesn't it? Like a lot of stuff on the front, a lot of stuff on the end, and then there's the data in the middle. Lots of wasted stuff. Don't try and figure this out. Eh? It's literally just garbage. All right. So just quickly, how do we send this stuff? We send it over Wi-Fi or Ethernet, don't we? Over a cord or over the air, okay? But we're not going to talk about that, guys, because that's just way too much detail.
So is this how they wire things online?
No. I actually don't know how that works. I would like to know. But guys and gals, this is the first concept, and it's a pretty complex one, so I'm going to take a little bit to explain it. This is the first way that we send data over a network. It is called TCP/IP. Has anyone ever seen those letters before? IP, yep. Hands up if you've heard of IP.
Do you?
Excellent, Ed. So what does it stand for? TCP is called Transmission Control Protocol. So in other words, how do we transmit this data? And IP is Internet Protocol. How do we send it over a big network? Does that sound okay so far? We've got ones and zeros. We want to send it over something. TCP/IP, his job is to make sure the data goes into this what's called stack, and I'll explain that in a second, and it comes out the other end ready to go over a wire or over the air. Okay, any questions at this point so far? All right, I will take our time and you guys ask me questions. But the first thing is, have a look at these numbers down here for me, boys and girls. This is what you call the TCP/IP stack. And essentially, it is all the layers that data has to go through in order to be sent over a network. And the data starts at layer 4 and it goes down to layer 1. And every time it goes through a layer, a little bit of data is added to it so it can be sent over Ethernet via electricity or, radio waves. So if you have a look at this top one, application layer, that's the thing that generates the data in the first place. Is it Google Chrome? Is it Fortnite? Is it Facebook? Is it whatever app you are using on your device? The application layer generates the data that is going to be sent. Everyone okay with that so far? The second layer, the transport layer, his job is to put a header on the front of our packet that says, this is the IP address and this is the protocol I'm using. And basically, that's where it's going to go. Okay, if I'm playing a game with Ben, if we're both playing Fortnite, and my computer needs to send his computer a message, then mine would literally say, go to Ben's computer, and put it on the front of the message. And that message might be, I shot Ben on the head. Okay? The next layer, the internet layer, this one's quite complex, but it basically breaks down how the hell do you get to Ben's computer. Okay? It puts another header and a trailer on it and says, this is where you're going, this is how you get to Mr. Ben over here. Network access, this is what turns it into bits or radio waves. So, in other words, it's going to go to bits and it's going to go, here's how I go through an Ethernet cable, ones and zeros, over to Ben. And once it gets to Ben's computer, this packet of data goes back through the stack, the opposite direction, and it strips away all that crap it put on there. So it's going to go that way now. So Ben's computer, first of all, collects all the bits. It then takes away all the address stuff because it knows where it is. It then takes away all the extra stuff there. And finally, it reads a message that says, you got shot in the head, he dies, he falls over, and he has to start again. How's that so far, everybody? Is that okay? Somewhat? That's like the roughest of introductions. That video series I was talking about, Jeremy's IT Lab, he spends 3 videos talking about this stack. It's incredible how difficult or complex it can get. If you want to know some terminology that you don't need to know for the course, going through this stack, top to bottom, is called encapsulation. You're encapsulating the data. Now I want to take a stab at the opposite. De-encapsulation. Yeah. Encapsulation, you're putting extra stuff around it. De-encapsulate, you take it away. All right, so there's our layers, everybody. Okay, and there's a bit more detail just on that next slide. Again, I'm going to pause because some of you guys have been doing a great job of listening. So, Year 12, just pause for me. Let's quickly move on to the next one. So, part of this TCP/IP layer, transmission control protocol, internet protocol, is the idea of a network port. Okay, when you have an application, so this might be you have an email program, you have Google Chrome, or you have Fortnite. Every app you run has to communicate over a port. Now here is the catch. Only one app can use one port number at a time. If you try and have two use the same port, Windows will basically go, nope, not happening, crash. Now just to quickly give you an idea, you might think, well that's very limiting, but have a look at this number for me right here.
Oh, yeah.
On a single computer, you have access to 65,535 digital ports. They are not physical things you plug into. They are just a number that you say, hey, Mr. Windows, can I please have port 1005? And Windows goes, no one's using it. Here you go. Sound okay so far?
Yeah.
No?
So what if all ports are being used?
Then you've got some viruses on your computer.
Oh, so is it ports per computer?
It's per computer.
Ah, so then two people can use the same port on.
And here's the thing too. So Sam, let's say you are communicating with me for whatever reason, you're sending me a file. Your application, let's say it opens up port 255 for whatever reason. You can, it's free. Windows goes, all right, Sam, have your port 255. When you connect to my computer says, hey, Sam, what port are we using? And you'll go 255. Mine then has to go, cool, I'm going to open up that port and connect to you. And then we can start sending through that port.
Yeah.
That makes some sense? Now you guys, what's that?
What if you've already got somebody on that?
If I've already got that port, Windows goes, nope, not happening, program crashes. Or if it's well written, it'll say, sorry, this is already in use. If it's well written. Now guys and gals, you do not have to remember these port numbers off by heart, thank God. But the most common ones that you guys guarantee you use almost on a daily basis, the first one, port 80, HTTP. Where do you usually see that?
Websites.
Websites, absolutely perfect. So that port is used for sending websites to people. So if you connect to youtube.com, you're using port 80 to download the web pages from YouTube. Port 123 is what you call NTP. That's how your computer synchronizes its clock across the web. Then the next one, IMAP. If you use an email client of any sort, you're using port 143, the IMAP port. And finally, HTTPS, okay, is secure web pages. Yeah, okay, it's a web page, but with a little bit of security on top of it. Okay, is everyone cool with that so far? Somewhat. Port numbers, 65,535 to choose from, one at a time. And there are, I think the first 1,000 you are not allowed to use. They are reserved for various things like HTTP, emails, stuff like that. You guys, if you make an app, and Doom is 666, if you guys would like to use other ports, you can. You can use port 2,000, 3,000, 4,000. So again, as long as it's not in use. Now, the IP part of TCP/IP is damn important. Taryn.
YouTube isn't what it's a HTTPS.
So it's 443. Thank you very much. Guys and gals, where have you heard of IP addresses?
Getting hacked.
Getting hacked. Beautiful.
Yeah, when someone you're playing with says, oh, I've got your iPhone, let's drink it. Oh, me too, I've got mine.
Alexis.
When you want to connect to someone else's game on the local area network.
Absolutely perfect.
Location.
Location. Now, guys and gals, there's a lot of misconceptions around this, so I'd like you to pause. Join me for a little bit. A lot of people think IP addresses are like this magic thing, no one can touch it, it's secure, whatever like that. However, let's go through a few concepts. First thing is, IP still stands for Internet Protocol, okay? A lot of people think it stands for Internet Position. It does not. Internet Protocol Address. What it is, just like every house in Australia needs a unique address so we can send you mail, every device on the internet must have a unique address so we can send it packets. And if you don't have a unique IP, we don't know where to send the messages. If there's two people with the same IP, how do we know where the message is going to go? So you must have a unique IP address. Now, if we quickly have a look down the bottom, there's two types of modern IP addresses, and I'm only going to teach you one of them, but I want to make you aware of the other one. There is IP version 4 and there is IP version 6. IP version 4 uses 4 octets of data. Now when I say octet, that's almost another word for byte. Okay, 4 bytes of data for IP4. And then for IP version 6, you got 16 octets or 16 bytes of data. Now, what am I on about? Well, let's have a look. That's a calculator, not what I wanted to open. All right, here it is, everybody. There is my IP version 4 address right there. I am now putting this on the internet, by the way.
10.2.
Oh, this is being recorded.
This is being recorded.
Are you gonna edit it out?
No, I'm gonna leave it.
Why?
I don't care if someone sees that. So, just a couple of things. I'm going to teach you how to do this and look at more information off camera because there are some settings I don't want the internet to see with the full version of this. That IP address, when I connected to the Wi-Fi this morning, there's a computer on the network called a DHCP. Now, don't stress about the term just yet. We'll get there. And my computer says to Mr. DHCP, "Oi, what's my address today?" And it goes down the list of all the IP addresses. And it goes, "Oh, this one's free. You are now 10.222.208.140. And every day I come in, my computer asks that question, what IP am I today? And it allocates me a new one. Sorry, Alexis.
What is the actual way you can use someone's IP address? Like, what is the issue with?
How do I get the geographical location?
Hold on to that question for me. I'll come back to that if that's all right. That's a very good question. Put the recording back. So each octet can range from 0 to 255. How many octets do we have in version 4? 4. Spot on. So imagine, there we go. The smallest IP I could make technically is 0.0.0.0. Yeah? No one. It's not allowed. You actually have to start, this octet here has to start at 1. And that's just a rule that they made up when they made IP addresses. The largest octet we could have is 255. So this is technically the biggest IP address I could make. Sound pretty good? Can anyone see a problem? It's pretty big. It's fairly big.
It's also a different number of digits.
It's fine.
Oh, but
No, it's-
one's zeros. Yeah.
That's our biggest problem, is it's finite, okay? So if you want to go through all the potential options there, with IP version 4, we have a maximum of 4.2 billion unique combinations for addresses. Sounds all right, doesn't it? That's a lot. What's the population of the world? 8 billion. And they say in first world country, people have an average of like 2-3 devices. We've blown way past 4.2 billion on the internet. However, that's why they invented IP version 6. It's something like 2 quintillion combinations. It is a ridiculous number. It's incredible. Hey? Oh, so IP version 5, apparently they tested out a unique video streaming technology. And it never sort of kicked off, so they just scrapped it, and that was apparently IP version 5. So they just skipped straight to 6. Because when they were testing it, they used the number 5 in all of their tests, and they went, oh, this is not working, let's just scrap that. And when they invented version 6, they just went straight to 6, rather than using 5. I don't know. I haven't looked at it. Yeah, but guys and gals, IP address, yeah, it's a ridiculous number, hey. We will die by the time we get to the IP version 6. All right, before we write more notes, everybody, let's open up the command prompt. Open up the start menu, type in CMD, open up the command prompt, type in IP config, one word, IP CONFIG, hit enter, and there you are. Yeah, this one's not going to work. So let's try again. Trace RT det newsouthwales.net. It must be my computer. It might be blocked in my firewall. But these are all the jumps. These are all what you call the hops that my computer are taking to get, there it is. It finally got there. So if you start off at the top, over here, so 10.222.208.1, that's essentially what you call the router of the Wi-Fi network. It's then gone to Kelso's, some kind of Kelso server. It's gone a bit further to the, oh look. WAN. It's there. It's then gone to this server, don't know what it is, we could find out with a bit of detail. It's then gone to the department network, to another server, to something else, to another server, and finally it's got to that debt login page that you use. So Trace RT allows you to sort of figure out, all right, where am I going to get to this place? And it shows you all the hops in between. Okay, so if you want to have a go at that, guys,